520 RPM, 520. That is 120 into 26 by 6. That is what I have done here. So 520 RPM. Now, what is to be remembered is that this change from 500 to 520 happens instantaneously. Why? Because that is in the electrical domain, and electrical time constant is of the order of few microseconds or at the most a few milliseconds, which means immediately once you change the frequency, the speed of the RMF will rise to 520. Will the rotor speed rise in such a manner? Actually, it will not, because this is in mechanical domain. It is actually the shaft of the motor. It has some definite mass, inertia, etc., which means it is in mechanical domain, and mechanical time constants of the order of few seconds, which means the machine will need some time of the order of few seconds to rise from 500 to 520. So immediately once you change the frequency, your FS speed immediately changes. FR continues to be the old value, which is 500. Now the relative motion is not zero. We have plus 20 RPM relative motion, which means when there is when the relative speed is 0, delta was a constant. When the relative speed is 20 RPM or a positive value, delta will increase. This you can visualize. This is rotating at 500. This is at a slightly higher speed, so it will move away from FR, which means delta is effectively increasing. Once delta increases, what happens? Delta is torque is proportional to sine delta. As delta increases, torque increases. What happens if the torque of a machine increases? The motor will accelerate. That's how we achieve speed increase in speed using true synchronous mode. Okay, so what you need after all, you just need an inverter which can vary the frequency. An inverter can easily vary the frequency using frequency modulation, as well as it can vary the voltage using pulse width modulation. So changing voltage or frequency or both is absolutely very easy for the inverter to do. Hope the concept is clear. And thus just by changing frequency, we are increasing or decreasing the speed of the synchronous motor. Okay. Now what if I want to reduce the speed? What if I want to reduce the speed? The answer is you have to reduce the stator frequency. Solution is reduce the stator frequency. Now consider a case, the same case as earlier. Let Fs be 30 Hertz. Number of poles is 6. What is the speed of? It is 600 RPM. This was also 600 RPM. Okay. Let the angle be. These are just values. Some arbitrary values I am putting. 30 degree. 600 RPM and 30 degree. I want to decrease the speed. What should I do? I will change the frequency. Earlier we increased the frequency to increase speed. Now I will reduce the frequency to decrease speed. What will happen? Your stator speed frequency has changed from 30 to 25 Hertz. What is the implication? This speed, the speed of the stator will now become just 500 RPM. And this happens immediately due to the same reason I explained in the previous slide. It is in the electrical domain, and hence electrical time constant is of the order of few microseconds. Okay, whereas this one will continue to rotate at 600 RPM. Why? That is in the mechanical domain. It cannot immediately change its speed because the time constant itself, the mechanical time constant itself is of the order of a few seconds. So your stator speed is 500, rotor speed is 600, which means the rotor will accelerate, go past the stator field. Now what happens? Earlier delta was measured from FR towards FS. The delta was positive 30 degree. Now using the same logic, if I measure delta, what happens? Now the FS is here and FR has advanced FS. Now your delta becomes negative. Let it be minus 20. Just some values I am giving. What happens to the torque? Since torque is proportional to sine delta, sine minus delta is minus sine delta, or torque is negative now. In this mode, torque is negative. What do you mean by torque is negative? Operation is in quadrant 2, second quadrant operation. And what is the peculiarity of second quadrant? It is forward braking mode. Forward braking mode. If a machine undergoes braking, what happens? The speed will reduce, and that's what we want. So how did we do that? We reduce the frequency to reduce the speed, and we increase the frequency to increase the speed. This essentially sums up what is called as true synchronous mode of operation. Very simple, but then it has some serious drawbacks, which we will see in the coming slides. Coming to, sorry, yeah. Now, we have a problem. See, delta, the torque angle delta is proportional to relative speed between Fs and Fr. So, when the relative speed is 0, that means the fields are stationary with respect to each other, delta remains a constant. If they are varying, delta will also vary. That is the logic. Now, imagine the machine is operating at 500 RPM. I want to change it to 1000 RPM. If the number of poles is 6, the frequency is 25 Hertz. Obviously, this would be 50 Hertz. Which means if I want to change the operation from 500 RPM to 1000 RPM, I will have to change the frequency from 25 to 50. The issue there is that if you give a step change in frequency, this is 50 Hertz and this is 25 Hertz. If you give a step change here, 25 immediately jumps to 50, then we have some issues. What is it? Now, what is your new synchronous speed? 1000 RPM. Because the moment you apply 50 Hertz, the speed will immediately change. It is an electrical domain. Whereas rotor speed is still at 500 RPM, the earlier speed. See, what is the relative speed between them? It is as big as 500 RPM, which means delta abruptly increases, or rapidly, abruptly increases. And what is wrong in that? If delta goes beyond 90 degree, see, as I told, delta rapidly and abruptly increases, and there is a definite possibility that delta can go beyond 90 degree as well. And if delta goes beyond 90 degree, machine will fall out of synchronism. Okay, we call it machine falling out of step. The machine will just stall. It will not work as a motor anymore. Is the concept clear? So what I'm trying to say is that if you increase the frequency in a stepped manner, there is a definite possibility that the machine can go into instability. This is one drawback of true synchronous mode of operation. Instability is inherent feature of true synchronous mode. So what is the workaround? Why this problem came? We were changing frequency in a stepped manner. Say 500 RPM was here. We wanted to change it to 1000 RPM immediately. Instead, what we do is we gradually go like this. 1000 is here, 500 is here. Instead of a step manner, we give a delay, and after some time, we reach 1000. So as what the machine sees is, it's not a abrupt jump from 500 to 1000. 500 becomes 550, 550 becomes 600, 600 becomes 650. So in gradual steps, we must change the frequency. So from 25 to 50 Hertz, we should not change it in a one step. What happens is it should go to say 28, 30, 32, 34, like that, go up to 50 Hertz. Instead of going in a single step, you give a phased manner, you increase the frequency in a phased manner. So that is a solution to the instability problem. Now, this is the true synchronous mode. We have, see.
Excuse me, sir.
Yes.
Sir, നമുക്ക് ഒരു question ഉണ്ട്, ഒന്ന് solve ചെയ്തിട്ട് നമുക്ക് class continue.
Sorry.
Sir, question എങ്ങനെയാണ്? Do you feel one could develop a mechanical inertia measuring equipment using the principle explained by you?
എനിക്ക് question വ്യക്തമായില്ല. ഒന്നുകൂടി ഒന്ന് വായിക്കാമോ?
Okay, sir. Do you feel one could develop a mechanical inertia measuring equipment using the principle explained by you?
Yeah, we can make it, but then there are 100 better methods to measure inertia than using a synchronous motor to measure inertia. In synchronous motor ന്റെ purpose അതല്ല, inertia measure ചെയ്യലല്ല. ഇതേ ലോജിക്കൽ വർക്ക് ചെയ്യുന്ന inertia equipments ഉണ്ടാവാം, പക്ഷേ ഈ മെഷീൻ synchronous motor യൂസ് ചെയ്തുകൊണ്ട് inertia measure ചെയ്യേണ്ട കാര്യമില്ല. പക്ഷേ ഈ ടെക്നിക്ക് തന്നെയാണ് യൂസ് ചെയ്യുന്നത്. പല മീൻസിൽ ഈ ടെക്നിക്കാണ് യൂസ് ചെയ്യുന്നത്. ക്ലിയർ ആണോ?
Okay, sir. Okay. Sir,
So,
വേറെ questions ഒന്നുമില്ല. നമുക്ക് continue.
yeah, sure.
Okay, sir. Okay.
So this is the block diagram of true synchronous mode of operation. So as I said, you need an inverter, okay, and we have a delay block here. This is what I said. If you want to increase the speed in a stepped manner from 500 rpm to 1000 rpm, this will cause instability in the operation of true synchronous mode. So we have introduced a delay block. It could be a first order delay or second order delay or third order, depending on the the factor of safety what you want. You can make a delay block. What the delay block does is what I have shown, from 500 to 1000, not in a stepped manner, in a slowly, gradually changing manner. So from omega star, which is your frequency command, you get your omega prime once it goes through the delay. From that, we can calculate the value of frequency. Remember, changing frequency will give you the change in speed, but we have to simultaneously change voltage. Why? Because V by F is proportional to flux. If we just increase frequency without changing voltage, the flux will weaken. That's not what we want. Wherever possible, the flux in the air gap of the machine should be, the value of the flux in the air gap of the machine should be at its rated value. So we change V by F simultaneously, and so that the V by F ratio remains at its rated constant value. So if change frequency to change speed, proportionally change voltage to keep the air gap flux at its rated value. So we change V. How does the inverter change the voltage? Pulse width modulation. And how does the inverter change the frequency? Frequency modulation. Thus, with an inverter, you will be able to change the voltage as well as frequency and pass it on to the three-phase synchronous motor. This is how a true synchronous mode of operation work. All you need is a simple inverter. Okay, and let's see the drawbacks first. The response is sluggish. See, I wanted immediately to change the speed to 1000, whereas it is taking several seconds to do that. Why are we introducing a delay? To overcome the instability issues. So instability issues, another thing. Either you have to live with sluggish response to avoid instability, or you welcome instability to improve the speed of response. So together this will not work. Coming to the advantages, you can see there is no feedback. Just a simple inverter is more than enough. Simplicity and cost is a great advantage for this method. Whereas one more advantage is there, that is, it does not need starting damper windings. It doesn't need starting damper. Why? I will take some 2-3 minutes to explain this, then I will go to the question answer session. So please bear with me. Why is a synchronous motor self-starting? Not self-starting. This I have explained in the last class. But anyway, see, this is the condition. At the time of starting, your rotor speed is 0. Rotor speed is 0. Whereas this is, say, 1500 rpm for a 4-pole machine. Okay, what happens is that delta abruptly increases. It will go from 0 to 360, again 0 to 360. In several cycles, it will go. The torque is a sinusoidal wave. Okay, since delta varies from 0 to 360, the torque takes a sine wave shape. Average torque is 0. This we have already seen in the last class. And not just that, the rotor experiences positive torque. For how much duration? It will be pi by omega s. As omega s is 1500, if you actually ignore the number of poles and reverse calculate it, and you will get approximately, this would be approximately, not exactly, I am saying approximately 10 millisecond. 50 hertz wave, 10 millisecond. So the rotor experiences a positive torque for 10 millisecond, then it experiences an equal and opposite negative torque for the next 10 milliseconds, and the cycle continues. Now, what is the problem here is that the rotor is a heavy piece of steel. It's an electromagnet kind of a thing. 10 millisecond is too small for the machine to react. Before the rotor could react to this positive torque, it is subjected to a negative torque here within 10 millisecond. Before it could react to the negative torque, it is again subjected to the next cycle of positive torque. Thus, a synchronous motor experiences a pulsating kind of a torque. Okay, so the average torque becomes 0. Why do we need dampers to do that? If we have dampers, dampers are nothing but these are solid copper bars embedded on the rotor poles, and they are short circuited, which means at the time of starting, a synchronous machine starts like a induction motor, a squirrel cage induction motor. Now what happens is that without a damper, this is the case. With damper, this is the case. Still, the average torque becomes 0. But see this time. So here it was pi by 1500. That was the time for which it was experiencing a positive torque. Here, what will be the case? Synchronous speed is 1500, and since it works as an induction machine now, the damper winding is doing that. It may reach a speed close to that, let's say 1480 RPM. See, this is pi by 20, which means a positive torque is there for a much more larger duration of time if you have dampers, which means the rotor gets enough time to react to this positive torque. Okay, so once it starts moving, what do we do? We give the DC excitation. Now the steel piece becomes a magnet which has north and south poles, and they will get magnetically attracted to the rotating magnetic field and gets locked. This is how a synchronous machine starts. And remember, what I am saying is that with a true synchronous mode of operation, you don't need starting dampers. Hunting dampers are needed. Okay, I think you understand the difference between these two. If anyone doesn't, please ask in the question answer session. I will explain that. Those who know it, please remember, starting damper is not needed if you are operating a synchronous motor in true synchronous mode of operation. However, hunting dampers are still needed. Okay. Now tell me, why do we say that we do not need dampers? We have understood how a damper works, but tell me why we do not need a damper in true synchronous mode of operation. Because the answer is that because we have an inverter. I will ask my inverter to give a voltage at 1 Hertz frequency. So what is the synchronous speed? 120 F by P is equal to, let P be equal to 620 RPM. Earlier it was 1500 RPM. That's why the rotor did not have enough time to react. It was only 10 milliseconds. Now it is only 20 RPM, which means the rotor now has enough time to react to the positive torque, and the rotor builds up speed. Now as it builds up speed, change it to 2 Hertz. Then 3 Hertz. Like that, build up to its rated value of 50 Hertz. So since we have an inverter which can vary frequency through frequency modulation, I do not need starting dampers. Okay, so this pretty much sums up the true synchronous mode of operation. Now, next 5 or 10 minutes, we will discuss your question and answer doubt, and then we will move on to the next mode of operation. If you have any doubts, please feel free to talk. Any doubts?
Sir, actually, pinna very doubt on the
Okay. So shall I move on to the next?
Sir, could you kindly explain as to why synchronous motor is more efficient than IM?
Okay. See, compared to an induction machine and synchronous machine, okay, the stator is same for both of them. The only difference comes in the rotor circuit. So what are the losses in the rotor circuit of an induction machine? You have slip losses plus other mechanical losses. How about synchronous machine? You definitely have mechanical losses here, but there is no slip losses. Why? Because there is no slip at all. The synchronous machine, as well as the synchronous machine's rotor, as well as the RMF rotates at the same speed. So the slip is 0. Hence, S times the air gap power, SPG, that is the slip losses, that is 0 for a synchronous machine. The absence of this slip losses makes a synchronous machine more efficient than an induction machine. Now you may ask me, see, synchronous machine has excitation losses because we have to feed in DC current to the rotor poles. Definitely that is there, but magnitude wise, that will be much smaller than this slip losses. Why? Because we are feeding, say, 220 volt DC, through maximum field current would be 1 or 2 amperes only. So maximum loss you can experience is hardly for less than 500 watts. Whereas slip losses will come into kilowatts of power for high power machines. That's why a synchronous machine is far more efficient than induction machine. Now we can get away with this slip loss as this excitation loss as well. How? Replace the existing rotor with a permanent magnet. Then since there is no DC current going into the rotor, the excitation loss also is 0. That's why EMSM machine is said to be the machine with the highest possible efficiency. So it's a permanent magnet synchronous machine. With the permanent magnet, I am making my excitation loss also 0. Slip loss is anyway not there. Clear?
Okay, sir. One question over.
Yes.
Do you feel this is why BLDC motor is more efficient?
Yeah, PMSM and BLDC are exactly the same. They are same. Only difference comes in the nature of the flux waveform in the air gap. It has a PMSM has a sinusoidal flux distribution. BLDC has a trapezoidal flux distribution. Okay, that's the only difference. Otherwise, they are essentially the same. Anything more?
Sir, okay, clear, sir, continue. Okay, sir.
Okay.
No other questions.
All right, thank you. Now we have seen the true synchronous mode. What was the reason for these troubles we face in true synchronous mode? Omega is not equal to omega r during transients, and this was the reason we had some problems in true synchronous mode of operation. Okay, so during transients, omega is not equal to omega r, then delta will increase, and there is a possibility that delta can go beyond 90 degree and causes instability issues. So that is the reason why we say this is the reason why this TSM true synchronous mode of operation has certain issues. Now, how can we make omega is equal to omega r even during transients? That is what is used in self-controlled mode. Now, do not read all this; you will not understand. Now, listen to me. In self-control mode, what we do is that we sense rotor speed. Okay. Once we sense the rotor speed, get the frequency. That is the frequency corresponding to the rotor speed. Use it as stator frequency, which means now the stator or the RMF follows the rotor speed. Now I will explain it with some numbers so that it will be clear to you. Let's say we have a 6-pole machine. Okay. NS is same as NR at 500 RPM. So which means your frequency is 25 Hertz. Assume that you load the machine. Suddenly you load the shaft of the machine. What happens is that your rotor speed now is 400 RPM. In self-controlled mode, what we do is that you sense the speed, you sense omega r, get the frequency from that. What is the frequency? 400 into number of poles by 120. So this would be 20 Hertz. Now the rotor frequency is 20 Hertz. Use that as the stator frequency. Now earlier stator frequency was 25 Hertz. Now it gets changed to 20 Hertz. So what is the new synchronous speed? 400 RPM itself. What did I say? Omega s and omega r even during transients should remain the same. So for that, this is the flow chart of the operations what we do. We sense the rotor speed, get the rotor frequency, and use it as the stator frequency. So even during transients, speed increasing or speed decreasing, omega s remains equal to omega r. In true synchronous mode, omega s was equal to omega r only during steady state. In self-controlled mode, omega s is equal to omega r always, even during transients as well as during steady state. Okay, at least I think most of you would be confused how to increase the speed of this machine. Now, if the stator itself is following the rotor, how can you increase the speed of the machine? That we will discuss in the coming slides. Okay, so understand, in self-controlled mode, the stator follows rotor. Stator follows rotor. Not in terms of delta. What I'm saying is that the rotor speed decides the speed of the rotating magnetic field, not the other way around. Earlier, the RMF speed was the rotor speed. Now it is just inverse of that. The rotor speed decides the stator RMF speed. Okay. Now, how to increase the speed of such a machine. Okay. Now for that, we go back to the basic torque equation of a machine. Motor torque is equal to load torque plus J d omega by dt. During steady state, this becomes 0. The speed term becomes 0. Tm becomes equal to TL. I want to increase the speed of the machine. To increase the speed, what should you do? Your Tm has to increase. That is, only if Tm exceeds TL, you can increase the speed of the machine. So Tm has to increase. How to increase the speed? How to increase the torque? Earlier, what we have seen in true synchronous mode, torque was proportional to delta. So we increase the stator speed to increase delta. Here we cannot do that. Why? Because the stator frequency is decided by the rotor speed. We absolutely have no control over that rotor frequency. If the stator frequency is something, if the rotor, what is the rotor speed? That dictates what should be the stator frequency. In true synchronous mode, frequency was the control variable. Here, frequency is not the control variable. It is an independent variable. So we cannot touch frequency to increase delta. Then what can we do? For torque to increase, your delta has to increase. What can we do? See, suppose the machine is operating with EF and V at an angle delta. Let it be 30 degree. Let it be 30 degree. Both are rotating at, say, 500 RPM. 500 RPM. This also at 500 RPM. I want to increase the speed of this machine to, say, 600 RPM. What am I supposed to do? Increasing delta directly, increasing frequency to increase the speed of this one is not possible, because what is the speed of the rotor? That dictates what will be the speed of the RMF. So in which other manner can we do? That's what we see. What is this voltage? This voltage V is impressed by the inverter connected to the synchronous motor. We have seen in the previous slide. What all things can an inverter control? We have seen it can control V through pulse width modulation. It can control F through frequency modulation. There is one third important parameter which an inverter can control, which is called the phase of the output. The phase of the output with respect to a reference also an inverter can control. We were using only the first two parameters in true synchronous mode, whereas we will be using this parameter in self-controlled mode. Okay, so with respect to EF, phase means it's always with respect to a reference. With respect to EF, I increase delta 2. Let delta 2 be 45 degree. Remember, the magnitude of the V is same. Frequency is also same because it is at 500 RPM. Then what is different? I am only synthesizing my voltage vector such that it is now 45 degree away from EF. Earlier it was 30 degree. Now delta has increased, because inverter could control the phase of its output voltage. Now what happens? Delta increases from 30 to 45. Sin 45 is more than sin 30. So your machine torque increases. If your machine torque increases, your speed also will increase. Now what happens? At 45 degree, this speed has increased to 600 RPM. Now what will happen? This is sensed. This is sensed. You extract stator frequency and apply it to voltage. So this also will rotate at 600 RPM. See, from 500 to 600, even during transients, the speed of the FS and FR both are same. That's why I said for a self-controlled mode of operation, omega R is equal to omega S, not just during steady state, even during transients, this is there. Okay. Now, we have seen how we control the voltage V, pulse width modulation, how we control frequency modulation. Now let's see how we control the phase of an output voltage. Okay. Consider, I understand it is a three-phase inverter. For simplicity's sake, I am considering only phase A. A, B, C, I am considering only phase A, or red phase, RYB. In that, phase R is being considered here. Okay. And this is the DC voltage. This is a single phase inverter. Load is connected between terminals A and B. And I am drawing the waveform of VA and B. Okay. My reference is this black line. I know this reference. And I have to synthesize my output voltage V at a phase displacement of theta degree. What should I do? Wait for the reference to come. Once the reference comes, wait for another theta degree. Once the theta degree passes, you switch on S1 and S4. What happens? The load VABC is a positive VDC. That's what is shown here. Positive VDC. Keep it on for 180 degree, then switch off that to turn on S2 and S3. What will happen? The load voltage is a negative voltage minus VDC. Okay, that again is for 180 degree. This cycle continues. What have you attained? This is your reference or zero crossing. This is a zero crossing of your output voltage. How much angle is the displaced? It is theta, and that's what we wanted. So if you know your reference, remember, if your reference is defined, then it's child's play for the inverter to control the phase of your output voltage. Hope the concept is clear. So frequency, pulse width modulation is for voltage magnitude. Frequency modulation is for frequency, and third parameter which the inverter can control is phase. That is with respect to a reference, which means your reference has to be properly defined. If it is defined, then the inverter can control the voltage magnitude, frequency, as well as phase of the output voltage with respect to that reference. Now, what is the significance of this reference? Okay. What is your EF? See, EF is this, V is applied voltage, inverter voltage is this, delta is the angle between them. Okay, and excitation voltage is a sinusoidal quantity. 0 to at 90 degree it takes its peak, 180 it comes back to 0, 270 it takes its minus peak, and 360 it comes back, and thus one cycle is completed. Now what does, suppose this angle is 90 degree, it is 90 degree as shown in the diagram. This is 90 degree. Now EF and V inverter are at a phase shift of 90 degree, or the phase of this output voltage is 90 degree with respect to EF. That is the meaning of this one. How to realize that? Wait for the positive zero crossing, negative to positive zero crossing, this point. Once this passes, wait for 90 degree more. Once 90 degree is over, turn on S1 and S4. Once you turn on S1 and S4, wait for 180 degree. Then turn on S2 and S3. And this cycle repeats. So here also it is S2 and S3. So thus, if you have your reference here, if you know your reference, then you can synthesize your output voltage at whatever phase you want. Hope the concept is clear. See, I'm coming to the back to this slide. Here I have shown delta 2, but here I have drawn 90 degree. What is the advantage of keeping this one 90 degree? Because torque is proportional to sine delta. If delta can be 90 degree, then torque has its maximum value. Torque takes its maximum value. So which means if you use such a machine, the best dynamic response is possible, because the machine, if it accelerates with its maximum torque. If it decelerates with the maximum possible torque. Thus, in minimum possible time, you can attain your new speed. Clear? Earlier, due to the delay block, it was taking so much time to reach the steady state. Here, with the least possible time, the machine will accelerate to its new speed. So, it's always best to keep 90 degree. Will there be instability issue? Absolutely no, because delta is completely in our control. If I say 90 degree, it will exactly operate at 90 degree, not a degree more than that. Which means still we will keep it to 85 degree considering some safety margin. But theoretically, even if it operates at 90 degree, it is fine. There is no worry of instability, because delta is the control variable now. In true synchronous mode, frequency was the control variable, TSM, stator frequency was your control variable. In self-control mode, delta is your control variable. Hope the concept is clear. Earlier you were varying the frequency, here you are varying the phase. That is the difference between these two modes of operation. Now, see, our reference is EF. Our reference is EF. How to obtain EF? Only if we know EF, then we can synthesize V. Otherwise, we cannot synthesize voltage. So, how to get EF? This is the voltage. This equation we have seen earlier also. If your answer is that you can substitute these values and get, then that will be wrong. Why? Because XS, synchronous reactance of the machine, is not a constant. It depends on the saturation conditions of the machine. You would have learned in your machine's course. Okay, so this is not a constant. It depends on the saturation conditions. Similarly, IS is not a constant. It depends on the temperature of the winding, the humidity, the skin effect, etc. So which means we cannot substitute these values and find out the value of EF. That is not possible. Can we put a voltmeter here? See, this is the EF angle delta. Okay, so can I put a voltmeter here and find out, or a CRO here and find out? Actually, that is also not possible. Why? Because this terminal is a fictitious terminal. This terminal does not exist in real life. See, this is the only terminal which is accessible to man. Here we apply voltage B. This EF sits behind the stator synchronous reactance. So which means this terminal is not accessible at all to a human being. We can only access this value. That's where we apply B. So measuring or calculating EF is not possible. Then how to do that? Because only if we know EF, then we will be able to synthesize V. To find EF, formulas will not help us. Voltmeter or CROs will not help us. Then what is the solution we have? That's what is called this EF is a function of the position of the rotor. Consider phase A. I am showing only, suppose it is R by B. I am considering only phase R, red colored phase A star. Let it be ABC. Okay. The phase voltage EF has its maximum value when the rotor is like this, vertical with north pole upwards. So EF has its minimum value, minimum in a sense 0. It's not minus EF, 0 value when it is horizontal like this. Okay, it means between this value and this angle, it traces a sine wave. Okay, from 0 to 90 degree. So thus, if the rotor position is like this, it will have some value in between these two values. Clear? So remember, we cannot measure the EF directly. We cannot calculate EF directly, but we have to obtain the value position of EF to synthesize the voltage according to that. According to that means we have to synthesize voltage 90 degree displaced with respect to EF. Displaced with respect to EF. So we have to know EF, then only we can realize voltage vector from the inverter. EF is a sinusoidal quantity. Remember, at 0, the poles are like this, horizontal. This is when I say horizontal, vertical, these are all relative terms, but still, for your sake of understanding, the poles are horizontal. Then it takes its maximum value at 90 degree when the poles are vertical with north pole upward. North pole upward. North pole is here. Then as it rotates further, it becomes 0 again, but there is a difference. North pole is towards your left side. Here, south pole was towards your left side. Okay. It is rotating in anti-clockwise direction like that. Then at 270, it takes its minus maximum value. Again, they are not same. The poles are vertical, but the south pole is now upward and north pole is downward. Here, so north pole was upward, and it comes back here. So just if you know the position, suppose, excuse my drawing, please. South, north. So if I know the position, I will be able to tell what will be the angle. Okay. Thus, if you know the rotor position, then you can predict the value of EF. That is the logic we are going to use. So to summarize, thus, if we know the position of rotor poles, we can reconstruct the EF wave. We can reconstruct EF. EF cannot be measured or visualized on an oscilloscope. So we are reconstructing EF from the knowledge of our rotor position. Who will give you the rotor position? That we will see in short while from now. To give the rotor position, we use a rotor position encoder. This is also called a sensor. This is the diagram of an actual rotor position encoder. This would cost somewhere around 3,000 rupees or something. Depending on different power levels, it is available. This shaft gets connected to the shaft of your synchronous motor at the non-driving end. At the driving end, you have your rotating load. At the non-driving end, you connect this to the motor. And through this, you will get to any rotor position encoder. This may be very complex RPE, but any encoder will give two parameters. One is theta. That is the position of the rotor poles. Second one is d theta by dt, the rate of change, time differential of this theta. What is this? This is nothing but the speed of the rotor. It gives speed, it gives position. These two signals will, any rotor position encoder will give. Present day RPEs can give much more data, but understand, if it is a rotor position encoder, then it should give speed as well as position. This you keep in your mind. Okay. So this equipment is used to get the position of the rotor poles. Now assume that the rotor poles are at 60 degree. Okay. At a given time, we cannot open the machine and see whether the rotor poles are. So we are using rotor position encoders. RPE says 60 degree. This is given by a rotor position encoder. This is 60 degree. Now if I know 60 degree, what all things can I say? 60 degree backwards, I had my EF zero crossing, positive zero crossing of EF. 30 degree from now, I will have my positive of EF. 120 degree from now, I will have my zero of EF, which means if you know where the rotor poles are currently, you can reconstruct the EF wave. This dashed blue lines, what you see is the EF wave. So just by having one point in the locus, you can reconstruct your excitation voltage waveform. Once you know that, what is to be done? Now I am here. Okay, I am at 60 degree. What does it tell the inverter? Wait for 30 degree more so that 90 degree comes. Then you turn on your S1 and S4. Keep S1 and S4 on for 180 degree, then S2 and S3 on. Then you repeat the cycle. Just you have to have the information on this point. Okay. In this specific example, it is 60 degree. So inverter will turn on S1 and S4 30 degree after this. Okay. Let's consider another example. And one more thing. What will be this frequency? This one. This also needs to be calculated. Who will give that? This is also given by the rotor position encoder in as d theta by dt or your speed input. Once you know your speed, you can calculate this frequency. So you know your frequency, which means in 30 degree or maybe 1 millisecond, like that. So you have to wait for 1 millisecond, then turn on S1 and S4, then turn on S2 and S3, like that. Consider another example where it is 150 degree, the rotor poles are at 150 degree, which means the poles are here. You can reconstruct your EF waveform, and this is how you need your voltage waveform to be, so that this is 90 degree. This is 90 degree. Now you are already at 150 degree. You are already at 150 degree. What does it say? I should have turned on my inverter at 90 degree itself, so turn it on. So S1 and S4 turns on. It has to be on till 270 degree. Now I am at 150, so wait for 120 degree more. Wait for 120 degree more. Once 120 degree passes, turn off these two, turn on these two. Keep them on for 180 degree, then turn off, keep them on for 180 degree, and the cycle continues. So just by knowing or just by having a rotor position encoder, you can construct your EF, you get your reference. With respect to your reference, you can synthesize your voltage at 90 degree from the reference voltage. So the problem of getting a reference is solved by using a rotor position encoder or a sensor. So without a sensor, a self-controlled mode of operation will not work. You need to have the knowledge of your EF, then only you can fabricate your voltage waveform. If this concept is clear, we are reaching the end of this one. This is the block diagram of self-controlled mode. Compared to a true synchronous mode, this has some drawbacks. Drawbacks in the sense it is much more complex than that. Remember, earlier we did not have any feedback, but here it will operate. A self-controlled mode operate only in closed loop. It cannot operate in open loop. Okay. Why is it so? Because the stator frequency is decided by the rotor speed. So we have to sense the rotor speed and then do all these things. Okay. So you have your speed command, your desired speed omega star. Actual speed comes from the rotor position encoder connected to the synchronous motor. An inverter is connected, a controller is it's governing the inverter, and here the error comes, the speed error comes. A PI controller operates on the speed error, produces delta prime, okay, delta dash. Since it is a PI controller, the delta prime may go beyond 90 degree. It is possible that delta may be more than 90 degree. Say, let's say 105 degree. We cannot give it because if it exceeds 90 degree, the machine will fall out of step. So we use a saturator to limit it to 190 degree. So if the output is, if the input is more than 90, output will be 90 only. If the input is less than 90, then it is as it is. For example, if it is 75 degree will come here. If it is 100 degree here, only 90 will come here, like that. Okay. So delta is limited to 90 degree, and that comes as your delta reference. Now the inverter will synthesize your voltage at a phase shift of delta. With respect to what? We need to have a reference. Who gives the reference? Again, RPA gives in the form of rotor position. With respect to this rotor position, your output voltage will be phase shifted by delta. Now, the speed, same speed is used as the feedback. As I said, the speed is sensed, the frequency is extracted, and that is used as the frequency command to the V by F controller. Once we know the frequency, we can find V so that V by F remains constant. So we have your frequency command, we have your voltage command, as well as your delta command. Now, it's very easy for the inverter to synthesize this voltage at this frequency, at this phase, with respect to this rotor position. Okay, so we control V, F, and delta with respect to the rotor position, and that will be impressed on synchronous motor. This ensures that your delta, your EF and V are displaced by an angle delta, and delta can be as high as 90 degree if you want maximum torque to be developed by the machine. Hope the concept is clear. So obviously, from the diagram itself, we can say it is much more complex than true synchronous mode. There it was open loop. There was no feedback needed. Here you have a rotor position encoder. You need feedback. You need PI controller, and all such complexities are there. But understand, the performance of a drive, of a self-control mode drive, is no match for that true synchronous mode of operation. This is the best you can get, because with this you can make your FS and FR 90 degree to each other, which means it is similar to a separately excited DC motor, and that's the best you can get out from a motor. So with a self-controlled mode and with a rotor position encoder, you can operate a synchronous motor very well like a separately excited DC motor. You cannot ask for more than this. Okay, so all the high performance drives what you see are run using self-controlled mode of operation. Okay, coming to the last slide. Yeah.
Okay, sir. The last slide. 5 minutes.
Okay, last slide.
Okay, sir.
Last slide. As I said, it is very much complex. You have seen the block diagram, and the presence of rotor position encoder makes it fragile. What I am trying to say is, consider a 1 megawatt machine that may cost 50 lakhs rupees, 50 lakhs, and the rotor position encoder, as I told, it may be available for 5,000 rupees, 5,000. The operation of such an expensive machine depends on this kind of a sensor. If this fails, if the rotor position which just cost 5,000 rupees fails, this 50 lakh machine is rendered useless. Can we say that that's a good design? Actually, no, because such an expensive and a very significant crucial equipment depends on a fragile equipment for its operation. That cannot be seen as a good design. So that's how sensorless controls, sensorless control. This is a new research area where several methods have already been discussed. You remove the RPE, but if you remove RPE, how can you get EF? There are several methods of predicting the value of EF. Several researchers have put forth their own theories and flowcharts to predict value of EF. So that is sensorless. So this drawback can be overcome in sensorless control, but then you lose. See, here they are predicting it. There is some chance of error. Here there is no chance of error. You are actually getting EF. So it's a trade-off between these two. And coming to the merits, you have complete control over delta. A delta, if you want it to be 90, you can operate it at 90. No instability issues. Omega S and omega R are same, even during transients as well as during steady state. Best dynamic response possible. you have your Tmax because delta is 90 degree. And as it is 90 degree, it makes the machine work like a DC machine. If any machine which can work like a separately excited DC machine, that is the best you can get from that machine. So self-control mode makes a synchronous motor work like a AC/DC machine. So that's all. I have overshot the time by some 5 minutes. Sorry for that. If you have any doubts, please shoot.
Okay, sir. Rented out ഉണ്ട്. ഒന്നാമത്തത്, can you explain the process, the hunting in synchronous machine?
Hunting. Okay, I will explain.
Sir, ഒരു ക്വസ്റ്റ്യൻ കൂടി ഉണ്ടായിരുന്നു. നമുക്കൊരു 5 മിനിറ്റ്സേ ഉള്ളൂ. ഓക്കെ, നമുക്ക് ടോട്ടൽ 5 മിനിറ്റ്സേ ഉള്ളൂ. സാർ ഒന്ന് വേണ്ടി പെട്ടെന്ന്
കഴിഞ്ഞു. ഞാൻ ക്വസ്റ്റ്യൻ ആൻസർ ചെയ്യാൻ റെഡി നിൽക്കാം.
ഓക്കെ, അപ്പൊ ഈ ക്വസ്റ്റിന് ശേഷം ഒരു ക്വസ്റ്റ്യൻ കൂടെ ഉണ്ട്.
ഓക്കെ, അപ്പൊ ഈ ക്വസ്റ്റ്യൻ പറയട്ടെ ഇപ്പോ.
ഓ ശരി സാർ. ഓക്കെ,
ഹണ്ടിങ് എന്ന് വെച്ചാൽ എന്താന്ന് വെച്ചാൽ, see this is a rotor pole and it's a huge inertia machine. It's made of steel. You have a lot of windings through it where you pass DC current, and this is rotating at a speed as high as 3000 rpm. Now the issue is that if this is your operating point and it is coming like this, it may overshoot due to inertia. Once it overshoots, it is pulled back by the rotating magnetic field. It comes back. Then it may, due to inertia, it may go little further. It may overshoot. Then it will come back. After a few oscillations, it will stabilize. These oscillations are called hunting. Okay, so to prevent hunting, there are damper bindings kept on all faces. Okay, so it's like a squirrel cage induction machine. Whenever there is hunting, you have relative motion between stator field and rotor field. So it works, and now the induction motion action takes in, and working on that difference in slip, it will try to nullify that slip. So remember, your starting damper and hunting damper both are different. Starting damper is used to start the synchronous machine because it is not self-starting inherently. Hunting damper is used to prevent hunting during load changes of the synchronous motor. Hope the concept is clear. So next question, please.
Okay, sir. One question ഉണ്ട്. Do you mean to say measure the rotor speed and adjust the PWM starting delay between 0 and 90 degree for controlling phase?
Repeat the question once again.
Sir, do you mean to say measure the rotor speed and adjust PWM starting delay between 0 and 90 degree for controlling phase?
Yes, that is exactly what is being done. You sense the speed, you extract the frequency component from that, use that as the frequency to the stator. Okay, for example, consider a 50 hertz machine. 230 volt is the phase voltage. Okay, now a rotor is rotating at some speed, correspondingly 20 hertz is the speed. Now, which means this will be your stator speed as well. Now, what is the ratio K? Is 0.4, 20 by 50. Now, what should be the voltage you must apply? 0.4 into 230. How much? What will be that? 23 into 4. 92 volt. I'm not sure. Let it be 92 volt. So this is your voltage and this is the frequency. And phase, you make it 90 degree. And the inverter can easily do this. So that's what is being done. Okay. So from where did we get this 20 hertz? Did we choose it? Actually, no. It is the frequency corresponding to your rotor speed. Why we do that? To make our stator speed and rotor speed same. That is the basis of self-control mode. That's all.
Okay, sir. ഒരു ഡൗട്ട് അല്ല, പക്ഷെ ഒരു കുട്ടി ചോദിച്ചാണ്, വിൽ യു ബി ടോക്കിംഗ് അബൌട്ട് വെക്ടർ കൺട്രോൾ ഓഫ് ഇൻഡക്ഷൻ മോട്ടോർസ് ഓൾസോ? സർ, ഇത് അടുത്ത ക്ലാസ്സിലായി ഉണ്ടാവുന്നതായിരിക്കണം.
As of now, I have not planned another session. I am expecting our courses will be opening next week, the week after next. So I am not sure on that.
Okay, sir. Sir, അപ്പം നമ്മുടെ സെഷൻ നമുക്ക്